This is Physics 1060, Lecture 2. Today we're going to start going through Chapter 2 material. So what we want to start here is trying to understand the sky. Astronomy is full of cycles, such as the day or the year or the month. And they're due to things like the rotation of the Earth, or the orbit of the Earth around the Sun, or the orbit of the Moon around the Earth. So in this section we're going to try to understand these cycles. This is possibly the hardest part of the course. It took civilization thousands of years to understand what's going on, so you really shouldn't feel bad if it takes you a couple of weeks. There's a simple reason for why this is difficult. We're trying to understand the apparent motion of moving objects, such as planets, when we ourselves are also moving, albeit a little slow for our senses to detect directly. So, the goals here are to understand some very complex patterns in terms of a few simple ideas. To be able to understand and predict how the sky appears. To learn how to use or draw diagrams as an aid to simplify ideas. And I'm doing this at an early stage of the course because I want you to watch the sky over the next few weeks. And so actually in some of the people in lab are going to be drawing pictures of the sky and are trying to understand why the sky moves the way it does. So let's start with night and day. The sky at night. We look around and we see vast numbers of stars surrounding us. Why don't we see the stars during the day? Most of what we see in everyday life is scattered light. Now, exceptions include things like electric light bulbs or the sun, which actually generates light rather than scatters it. So, for example, a light bulb here, electrical current's going through the filament and it's giving off light. It's generating light. Whereas if I were to look at some object sitting on the table in front of you, we might not see light being given off from it. What happens is light from a generated object comes and strikes that light and scatters it off. So in astronomy it's very important for us to distinguish between objects that generate light, for example the sun or the stars, and objects which scatter or reflect light, such as the moon or the planets. The sky is bright during the daytime because light is scattered in the Earth's atmospheres. Actually, air molecules here are very good at scattering blue light. They'll let the reds and yellows go on through, but the blue light from the sun that comes and strikes them is absorbed and re-emitted in all different directions. So when we look up at the sky, what we see is blue from the blue light being scattered by the air molecules. Now if we look at a photograph of the astronauts on the moon, we see that the sky is dark, even though the sun is out and casting a shadow here. In fact, when there's less atmosphere above you, the sky looks darker. If you ever have a chance to be in an airplane and sit by the window, crook your head over and try to look up. You're going to see that the sky is dark blue. Now clouds scatter light more, so they're brighter than the blue sky. We exist in a universe that there are stars all around us. The only reason we don't see them in the daytime is that the sky around them is too bright. However, with some kinds of telescopes, we can see the stars even in daylight. Now this atmosphere that the Earth has doesn't have a sharp edge. It trails off gradually, so really the pressure is down to about half of sea level at 7 kilometers. In fact, if we look at this picture of the Mir spacecraft, we can see this thin blue line here of the Earth's atmosphere. It doesn't really have a sharp edge, it just fades off into space. If you were to go into Hawaii and get on the summit of Mauna Kea, you're actually above a third of the Earth's atmosphere by mass. The International Space Station orbits at about 100 miles, which is pretty small compared to the diameter of the Earth, which is 8,000 miles. But in human terms, the atmosphere there is almost like being in a perfect vacuum. However, there are still traces of the Earth's atmosphere even at that altitude. So if we're going to try to understand the sky, we're going to consider the Earth in the middle of a three-dimensional forest of stars. And we're going to forget about the sun, planets, and moon, and ignore the rotation of the Earth right now, and try to understand the celestial sphere. Now just by glancing at the sky, we don't know the distance to stars. To measure distances to the stars, we have to make careful observations with a telescope, and we'll learn about those later. What we see is what looks like a pattern on the inside of a sphere, which we call the celestial sphere. We can make maps of the patterns of the stars, And from the surface of the Earth, we can never see more than half the sky at the time, but we can piece together an atlas of the whole sky. Now there's problems with making maps of large regions of the sky on a flat sheet, and they're the same problems that geographers face making maps of the curved surface of the Earth. And the positions of stars relative to each other change very slowly. Although the position of the stars relative to the horizon changed by the hour, as we're going to learn later. So ancient astronomers saw almost exactly the same patterns we do thousands of years ago, and they called those patterns constellations, and often linked them with their mythology. So the picture here is of Orion, and we see Orion's two shoulders, we see his legs, and we have his belt and his sword. Over here we have Taurus the bull, his eyes and nose and his horns, and so on. Now, the stars in Orion look close together, but they may not actually be very close together. They're not necessarily the same distance from the Earth, and probably are quite unrelated to each other. For example, even in the constellation Orion, we see his shoulders, we see his belt and his feet. We see that if we actually look at actual distances away, they're quite far away from each other. Angularly, they're close together, but actual distance apart, they're quite far. So the whole sky is divided into constellations, just like the USA is divided into states. And we use those to say, hey, I saw something in the sky, maybe you should go look at it. And you might ask, well, where is it? Well, it's in the constellation Virgo, so you'll know where to look in the sky. Now, of the stars, only the brightest stars have names. And in the West, these names are often derived from Arabic names. Most stars are referred to either by number or even just by their position in the sky. Millions have numbers, billions more exist on photographs and have never been given names. So, in describing the star's appearance, we need to discuss angles between stars. We can talk about one star being 10 degrees from another. This has nothing to do with how many miles or light years they are apart from each other, only the angle on the celestial sphere. So I have star here, and I don't care how far apart they are, but as I'm looking at them on a celestial sphere, I'll say there's a certain angle between them. We use degrees for large angles, and for small angles we use arc minutes. An arc minute is 1/60th of a degree, or arc seconds, which is 1/60th of an arc minute. The sun and moon both look to be about a half a degree, or 30 arc minutes, across the sky. A penny held at arm's length is about 1 degree, depending on your arm. So is your thumb. If you hold your thumb out at arm's length, it should be about 1 degree. Now, the coordinate system that astronomers use is a lot like latitude and longitude. I don't need you to understand how to use it in this course, but I just want you to understand what it is. And like latitude and longitude, the coordinates then are based on angles. So now let's add the daily rotation of the Earth. We're going to continue to ignore the sun, moon, and planets. We're just going to look at the fact now and what changes as the Earth rotates around its axis once per day. This picture here is a time-lapse picture of about 8 hours, and we can tell because these arcs are about a third of the way around a circle. So a third of 24 hours is about 8 hours. So the stars appear to rotate around a point in the sky. Now, that imaginary point above the Earth's North Pole is called the North Celestial Pole, and it's very close to the location of a star there. We call that star Polaris. There's also a South Celestial Pole, but there's no star there, so there's no South Star. Now, any stars that are equidistant from the two celestial poles are called the celestial equator. If we look down onto the Earth from above the North Pole, the Earth appears to rotate counterclockwise. In other words, it rotates towards the east. Stars, therefore, appear to move from east to west in the sky. So how are we sure the Earth is rotating and not the celestial sphere rotating around us? Well, we can do a test with an instrument called a Foucault pendulum. You'll see these often in science museums, or even in the NNU Science Building. We have one in the front lobby. It's a large mass that oscillates slowly, and over the course of the day appears to rotate. So Foucault was a Frenchman in the 19th century who built this large pendulum with very low friction, which could keep swinging all by itself for several hours. When you watch a pendulum, you'll notice that the plane of its swing appears to rotate over the period of hours. Now, it's easiest to understand this if we imagine a Foucault pendulum built right at the North Pole. Once the pendulum is swinging, it stays swinging in the same direction in space, even as the Earth rotates underneath it. If the Earth was fixed and the sky actually rotated, then a pendulum would not appear to rotate with respect to the Earth. Now, what about visibility of stars? Until now, we have ignored the fact that when we look at the sky, the Earth itself hides half of the universe. Half the universe is above the horizon and half below it. So in this section, we're going to examine how the appearance of the sky changes with your location on the Earth and with time. So first, our variation with latitude. Latitude of a place on Earth describes its north-south position. Idaho has a latitude of about 45 degrees north. Lines of latitude run from side to side on a map. The angle between the horizon and Polaris, or the North Star, is equal to your latitude. So, if I look out at the horizon and I measure the angle that I see up to Polaris, that is going to be my latitude. And here I have a picture using some planetarium software of what the sky looks like in several different places. And you can't really read it on here, but this picture here, the star that has the label next to it is Polaris. We see how high Polaris is. It's about 45 degrees above the horizon in Nampa. Whereas if we go over here to Mexico City, Polaris is much lower in the sky. Or up north to Fairbanks, Alaska, Polaris is much higher in the sky. So Polaris changes height at different locations on the Earth. If you stood at the Earth's North Pole, you'll always see Polaris directly above you, ignoring the brightness of the daytime sky, of course, with the sky rotating around Polaris. The same stars are visible above the horizon at all times. No stars ever rise or set if you're at the North Pole. If you stand at the equator, Polaris is right on the horizon, and all stars will rise and set. In principle, you can see all the stars in the universe at some time or another, although only half will be visible at any time. And then the celestial equator is going to run directly overhead from east to west. So if you stand at an intermediate northern latitude, you're going to see Polaris at some angle above the horizon that's equal to your latitude. Some constellations then near Polaris are visible all through the night. They're called circumpolar. The Big Dipper is a circumpolar star at our latitude. So some constellations near the south celestial pole are never visible. Most constellations can be seen some of the time as they rise in the east and set in the west. Now what we see at night also changes with longitude. Remember, longitude describes the east-west position of a place on Earth. London, or Greenwich, England, is at latitude 0, and NNU is roughly around 116 degrees west. All stars, except for Polaris, move from east to west. They cross an imaginary line in the sky called the meridian. The meridian is a line that starts due south, passes directly overhead, which we call the zenith, and meets the horizon due north of you. So at any time of night, the exact appearance of the sky depends on your longitude as well as latitude. Stars rise at different times at different longitudes on the Earth. So for example, if I were to look at, say, in LA and in Honolulu, and I were to look at the meridian in LA and the meridian in Honolulu, this star here has already crossed the meridian in LA as the Earth is rotating around this direction, but has not quite passed the meridian in Honolulu at the same time. So the same star crosses the meridian about 15 minutes later in Nampa, then in Seattle, about 2 hours later than in Chicago. Crosses Honolulu about 2 hours later than LA. Now when does the sun cross the meridian? Well, noon, or solar noon, or midday used to be defined as the time the sun crossed the meridian, but that changed with the introduction of world time zones. Time zones came about because of things like the railroad. A railroad conductor might have to keep very strict schedules because trains share tracks, and you don't want to be on a train going east when one coming west is on the same track. So, at every train station there was a clock, and in the clock there's a building that maybe has a slit in the roof at some point, and when the light from that slit comes and strikes a line on the floor directly underneath, you know it's exactly solar noon. And say a train was in Boise and was going to Nampa. Well, there's 6 minutes difference there, and so what a conductor would have to do is set his clock in Boise, and then on the way to Nampa, he would have to know to set his watch forward 6 minutes so he arrived in Nampa on time. This became very confusing, and so we introduced these time zones where we said it really doesn't matter if you're a half hour off solar noon. No one really cares. So we're going to divide the world up into 24 time zones. The middle of the time zone, noon, will happen at exactly the right time, and as you go away from it, a half hour each side, you'll be off differently. Now that was great, but not everyone wanted to be in their proper time zone because of political reasons. So for example, if I were to point out Nampa is over here, right on the edge of the Mountain Time Zone. We're actually about 20 minutes into the Pacific Time Zone, but we wanted to be with Mountain Time Zone for political reasons. That means that in Nampa we have very late evenings. The sun, it'll still be light outside in the middle of the summer, maybe out to 11 o'clock at night. Whereas if you're just over the line and you're in, say, Ontario, Oregon, it's only going to be light to about 10 o'clock at night. Now, it is, in principle, very easy for a navigator to determine his latitude on the Earth. You just need to measure the angle between Polaris and the horizon. If you couldn't see Polaris, you could use some other stars and make some calculations, but the principle is the same. It's much more difficult to measure longitude than latitude. If you want to determine the difference in longitude between two places, say between Honolulu and LA, using the stars, we need to know the difference in times that a particular star transits. If we're in Hawaii, we therefore need to know what the time is in LA. Until the time of Captain Cook, that was impossible since there was no radio and clocks were inaccurate. They only had pendulum clocks, which don't work very well at the sea. So only after the invention of an accurate spring-loaded chronometer by Harrison in the 18th century it was possible to measure your longitude at sea with confidence. It's a fascinating story. There's a book called Longitude by Davis Sobel that has the story of Harrison that if you're looking for an interesting book to read this summer, that might be it. Of course, today most people navigate by receiving signals from the GPS satellites. It's 24 satellites that are in 12-hour orbits around the Earth. You can buy a receiver that'll give you your position to less than 10 meters for about $100. Now, historically, our measurement of time was always based on the rotation of the Earth. Now that we have very accurate atomic clocks, we find there are small variations in the rotation speed of the Earth, probably due mainly to changes in the motions of the molten iron core inside the Earth. Astronomers keep track of the rotation of the Earth and decide when we need to add or subtract an extra leap second onto our clocks. Leap seconds, if they're needed, are usually added at the end of the year and announced well in advance. Most of you would never know because computer software automatically updates your clocks. In this section now, let's consider the consequences of the Earth's revolution around the Sun once per year. We're going to come back later to the controversy of how we know that it's the Earth moving around the Sun and not the Sun moving around the Earth. So as the Earth moves around the Sun appears to move against the background stars. When the Earth is in this location, and there's some stars here, the Sun appears to be amongst these stars. But as we move around, now the Sun appears to be around these stars. The Sun is not actually moving. It's the Earth moving around the Sun that appears to have the Sun move. So as the Earth moves around the Sun, different constellations are visible at night. The appearance of the sky just after sunset is thus different at different times of the year. Say January 1, when the sun is in Sagittarius, Gemini will be overhead, whereas March 1st, when the sun appears to be in Aquarius, Leo will be directly overhead at night. So, as the Earth moves around the sun appears to trace a path through the sky, and that path that the sun traces is called the ecliptic. It has nothing to do with ellipses or eclipses, it's just a name. And note that the constellations that the sun passes in front of are the signs of the zodiac used by astrologers. Now, the direction of the revolution around the sun is the same as the direction of rotation around the Earth, ignoring the 23.5 degree tilt for now. So if you look down from above the North Pole, the revolution and rotation of the Earth are both counterclockwise. And later on in the course, we're going to find that many other bodies in the solar system show the same sense of revolution and rotation. And this rotation is a clue of how the solar system is formed. Now, there's a number of important effects that are caused by the fact that the Earth's rotational axis is tilted with respect to its orbit around the sun. So the Earth is tilted slightly on its axis as it orbits the sun, and the tilt is 23.5 degrees. So, at this time of year, when the northern hemisphere tilts towards the sun, and the southern hemisphere tilts away, you notice there's this place, even as the Earth rotates, it's never going to get the sun, and a place that's always going to get the sun. The northern hemisphere gets more sunlight. Whereas over here, when the northern hemisphere is tilted away, the northern hemisphere is going to get less sunlight. The value of this tilt was set at the time of the formation of the Earth. The Earth's axis points in the same direction throughout the year. It points towards Polaris. So as it goes around, sometimes it'll be pointing towards, sometimes pointing away from the sun. And that means we're going to get more or less sun in different latitudes, and we get our seasons. So the sun's position on the sky changes from north to south of the celestial equator and back as we go through the year. The sun is actually on the celestial equator September 21st, the autumnal equinox, where we have equal day and equal nights. The sun gets furthest south on December 21st, or the winter solstice, where the sun appears to stand still. And then it gets back to the celestial equator on March 21st, the spring equinox, and it gets furthest north on June 21st, the summer solstice. So, a side note, the seasons are reversed then in the southern hemisphere. And once again, this is due to the tilt of the Earth's axis. So, do Australians dream of a white Christmas? Probably not. It's midsummer. So, what happens is the sun is higher in the sky in the summer as it moves north of the celestial equator. That means the ground gets hotter. If you're near the equator, the sun will pass to your south in December and to your north in June. If you're on the Tropic of Cancer at 23.5 degrees, the sun will always pass to your south at noon. And we can see then why we have seasons if we look at the sun in the summer and winter. So this top picture is what it would look like in the summer. So this is the celestial equator. It starts due east. The sun in summer actually rises a little north of east. And as it traces this path in the sky, it's always north of the celestial equator and sets north of west. So the path that it takes is very long. You get a lot of sun. Whereas in the winter, when the sun is south of the celestial equator, the sun will rise south of east and come and follow this path and set south of west, and it's not in the sky as long, and so I get less energy from it. It's cooler. On the equinoxes, the sun rises and sets with on the celestial equator. So as we move from summer to winter in the northern hemisphere, the positions of sunrise and sunset move southward. It's really easy to monitor this. Above the Arctic Circle, the sun becomes circumpolar in the summer, so that the sun does not set below the horizon. and in the winter it doesn't rise above the horizon. Now, the elliptical orbit of the Earth causes it to be a bit nearer to the Sun in December rather than June. And this effect on our climate is much less than the tilt of the Earth's axis. So we're actually closer to the Sun in the northern winter than we are in the northern summer. The Earth is actually pretty circular. This elliptical orbit is really deceptive. It's almost perfectly circular. It's just slightly elliptical, and we'll come back to that later. So the next thing I want to talk about is phases of the moon. The object of this section is to understand why the moon looks different at different times of the month, and why it is seen at different times of the day at different times of the month. So first, the moon takes about 29 days to orbit the Earth. The orbit is in the same sense as the rotation of the Earth and revolution of the Sun, namely it's counterclockwise when viewed from above the Earth's north pole. Its orbit around the Earth is tilted a few degrees from the plane of the Earth's orbit around the Sun. And that's going to be important when we try to understand eclipses. So the moon does not produce light. It reflects light. So the changing appearance of the moon is caused by the changing angles of illumination from the Sun. When the illumination is mainly from the back, we see a crescent moon. When it's mainly from the front, we see a gibbous moon. Crescent is less than half lit, gibbous is more than half lit. So at new moon, the moon passes between the Sun and the Earth. Because of the tilt of the moon's orbit with respect to the Earth's orbit around the Sun, they're usually not perfectly aligned, so eclipses occur only rarely. At true new moon, only the back of the moon is illuminated, so we do not see it. Conventionally, we often refer to the moon as new when the first crescent is visible a few days after a new moon. The first sighting of a crescent moon after the true new moon is of great significance to the Islamic religion. At this time, we can sometimes see the dark part of the moon faintly illuminated by light reflected back off the Earth. So, as we move through the month, the moon waxes, meaning its illuminated fraction increases, through the first quarter, 1 week, to full moon after 2 weeks. It's first crescent and then gibbous. So from full to new, again, the moon wanes through gibbous as far as the third or last quarter, and crescent new moon. So as seen from the Earth, we have a new moon. We can't see any of it. It's waxing crescent here. It's first quarter. It's waxing gibbous here. Becomes full, and then it starts to wane and get less light. So it's waning gibbous here. It's third quarter. And waning crescent, and then back to new moon. And what we see and when it rises and sets is going to change. So for example, if I'm standing here right at sunrise, the third quarter moon will be directly overhead. At sunrise, a full moon will be just setting, and a new moon will just be rising. So by looking at this, if we see the sunlight coming through, we can see at different times, for example, at midnight, a full moon will be directly overhead, or a first quarter will just be rising, or a third quarter will just be setting. So when can you see the moon? Assuming that you're in an ordinary part of the Earth, not near the poles. So at new moon, the moon passes between the Sun and the Earth, but because of the moon's orbit with respect to the Earth, they're usually not perfectly aligned, so eclipses occur only rarely. First quarter is seen in the evening, a full moon is seen all night, last quarter moon is only seen in the morning, and a new moon is essentially invisible. If you ever want to use a telescope to view the moon, first quarter is the best for looking at the moon. Now, the moon keeps the same face always pointing towards the Earth. That's why we can, in principle, recognize the man in the moon. The only people who have seen with their eyes the back of the moon are astronauts that have been in orbit. We're going to discuss reasons for locked rotations later in the course, but essentially the the moon's rotational period is the same as its orbital period. The moon rotates once for every time it goes around, so the same side is always pointing towards Earth. So this picture here is going to give you some idea of the scales. So here we have Earth and the moon. This is not how close they are to each other, but it shows you kind of an idea of how big they are compared to each other. The Earth's diameter is about 8,000 miles, 13,000 kilometers, and the moon's diameter is about a quarter of that. The Earth-Moon distance is about 400,000 kilometers, or 30 times the Earth's diameter. So eclipses occur when the Earth and Moon are well enough aligned to form shadows on each other. A solar eclipse occurs when the Moon comes in front of the Sun. These are pictures of an annular solar eclipse in October of 2005. It's annular because the positions of the Moon and Sun are such that the Moon is actually a little too close to the Earth, and so it doesn't actually block everything away, and so we see an annual of light around it. Sometimes it's a total eclipse, sometimes it's only an annular eclipse. So the angular diameter of the Moon is almost the same as the Sun, so they have to be almost perfectly lined up to see a total eclipse. A total eclipse only lasts a few minutes, however the effect is spectacular. Solar eclipses can only occur at the new moon. A lunar eclipse occurs when the Earth comes between the Sun and the Moon, and so the Moon looks darker, almost a blood red. A lunar eclipse is visible from half the world, and they can only occur at a full moon. The Moon is still faintly visible during the total lunar eclipse because of scattered sunlight from around the edges of the Earth. The Moon shines then with a faint red light because remember the blue light is scattered out of the Earth's atmosphere. So this figure shows us how we can see why we sometimes have eclipses and sometimes not. Because the Moon's orbital period is tilted at 5 degrees with respect to the Earth's orbital rotation around the Sun. So at this point in time, the Moon is below the Earth, and so the shadow of the Moon during a new moon goes below the Earth. Or the shadow of the Earth goes underneath the Moon, so you don't get a lunar eclipse. And the same thing happens over here. But certain times of the year, February and August mostly, even though it's tilted, the planes line up. And if that's the case, then we'll get a solar eclipse when there's a new moon, or we will get a lunar eclipse during a full moon. Now if you go to some NASA websites or spaceweather.org, you can get some pictures of what different annular or solar eclipses are going to look like. This is the 2010 annular eclipse. And you can see a map here, and it shows you where you're going to be able to see the annular eclipse, where you're going to be able to see some of the sun blocked. In this case, we noticed that it was visible in Africa and in China. Most of it was out in the ocean, the Indian Ocean, so most people didn't get to see this eclipse. The 2012 eclipse, this is a time-lapse picture of the eclipse. It was a total solar eclipse. And as we can see, it was visible briefly in Australia, but most of the eclipse was only visible out in the middle of the ocean. So since the Earth is mostly ocean, a lot of the times we can't see an eclipse on someplace on land. If you ever have a chance to see an eclipse, I highly recommend you go see it. There's lots, though, online, great pictures of the eclipse. This is pictures, this were taken in Iran, and this is the 2010 eclipse. You got this picture of the bird. There's another picture taken by the same photographer as a flock of birds came between the sun during this eclipse. These are pictures of the annular eclipse. Remember, annular means that not all the light or not all the sun is blocked. So for more information about eclipses, visit the website eclipse.gsfc.nasa.gov/eclipsehtml. And that concludes Chapter 2.